Okay, so for this second part of the problem, we're asked to take this operator f, which appears in our unitary operator, and set it equal to the momentum operator, which I've written here in the x representation, right? And we're also asked to take this small epsilon to be a small distance in space divided by h bar. And then we're supposed to show that psi evaluated as some x plus delta x can be written as this unitary operator acting on psi of x. So in order to do this, we just take our left-hand side here and we expand it. We write this as, well, let me say this is approximately equal to. So I have this here is approximately equal to psi of x plus delta x d psi dx, right? And now the right-hand side here is equal to 1 plus I epsilon f times psi of x, right? But now if we insert what this here is, this is psi of x. We have a plus I and a minus I from here, so those two cancel. Then we have an h bar and a 1 over h bar here. So all in all, we just get delta x times d dx of psi of x, right? So when I just insert my epsilon here and my f from here, I just find exactly this. So now we've shown that the left-hand side and the right-hand side are the same. So that's that problem. So, but this in turn implies that the momentum operator here is a generator of spatial transforms, understood in the sense that if we take this unitary operator, which is made from the f operator, and act on psi of x, we get psi at x plus delta x. So we can think of this as really generating spatial transformations. And then in the same way, we are asked to show what is the generator of translations in time. Okay, so what we know from previous lectures and exercise sheets is that we have a unitary operator which is related to time, and this is a time evolution operator. So this is e to the minus iht over h bar, right? Now if we take this and we take, let's say, instead of having t here, we take delta t. So we take a very small amount time here. So then we can expand this and we say this here is 1 minus I h delta t over h bar, right? So I've just expanded this to lowest order in delta t. Now if I define, let me define this epsilon as delta t over h bar in exactly the same way that I defined epsilon equal to delta x over h bar in the above problem. Then we see that we have exactly the same structure, right, as we did above. In other words, this here is equal to 1 minus I h times epsilon. So in other words, just like the momentum operator is a generator of spatial translations, the Hamiltonian is an operator of time translations, or the generator of translations in time. Okay? So I think that concludes that problem.